Okay, today we're going to talk about two more tests that we can use to determine whether a series converges or diverges. And the first one we're going to talk about is called the integral test. And the integral test basically says if you have a function f and these three conditions are true. First of all, it must be positive for all x's that are greater than or equal to 1. Second of all, so let me put a 1 by this. That's the first condition. Second condition is it must be continuous. Can't have any vertical asymptotes or jumps or holes. It must be continuous. And it must be a decreasing function for x is greater than or equal to 1. These are the three conditions, and you have to prove that these three conditions are true before you can apply the integral test. After you prove the three are true and you use the integral test, basically it says that the series, which is represented by the summation of n equals 1 to infinity of a sub n, and the integral from 1 to infinity, so this is an improper integral, of f of x, either both converge or both diverge. So, if you prove that these three conditions are met, and you use the integral test, if you take the integral of this series, which we'll write it like this, 1 to infinity of, we'll just say x over x squared plus 1 dx, if this integral, if you get a finite number, then that means that the series will converge. If you get an infinite number, so if you get infinity after you do the integral, then that means that this series will diverge. Now, let me make sure that there's one thing that's very clear, and this is extremely important. Let's say that you do the integral and you get 5 as an answer. That does not mean that the sum of this series converges to 5. All right? It just simply means that the series converges. So let's start proving that we are able to use this integral test. Condition number 1, it must be positive. Well, let's just say that we have the function x over x squared plus 1, and this must be positive for all x's that are greater than or equal to 1. Well, we can see that if we have an x that is greater than or equal to 1, the top is always going to be positive, and anything you square is going to be positive, and when you add 1, it's still going to be positive. So the first condition is met. It is indeed going to be a positive function for all x's that are greater than or equal to 1. The second condition we have to prove is that it is continuous. Once again, we can take a look at this function, and we see that there is no number that you could plug into the bottom that would cause you to be dividing by 0, because you're going to be squaring x and adding 1 to it, which will never equal 0. So therefore, this is definitely a continuous function. And then the third thing that we have to prove is that it is decreasing. And this is where you have to do a little bit of work. And for this, you're going to want to do the first derivative test. First derivative test. So we're going to use the quotient rule, and we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that over the bottom squared. So when you clean up the top, you're going to have x squared minus 2x squared plus 1. So you're going to have a negative x squared plus 1 over x squared plus 1 squared. Once again, you can see that any x that you plug into this function, any x that you plug in here or here, the top is always going to be negative, because when you square it and then you put a negative in front of it, it's going to stay negative. Plus 1 is going to be negative. And the bottom is always going to be positive, so therefore f prime of x is always going to be less than 0 for all x's that are greater than or equal to 1. So now that we've proven that you can use the integral test, let's go over here and let's actually figure out what this integral is. So we're going to integrate, and we see that we can use a u substitution. So we're going to let u equal x squared plus 1. So du is equal to 2x dx. So du over 2x is equal to dx. And so we're going to replace this with x over u times dx, which is du over 2x. And technically, we're supposed to be writing this as the limit as, let's say, b approaches infinity. And so we'll be good mathematicians, and we'll put a b up there. And so we see here that the x's will cancel, and we're going to bring the 1/2 out in front of the integral. So we'll have the limit as b approaches infinity, 1/2 of the integral, and I'm going to go ahead and integrate 1 over u, which will be the natural log of u, and this is going to go from 1 to b. So we have the natural log of u, which we called x squared plus 1, and there's a 1/2 in front of this. And so we're going to plug in our b, and b is infinity. So we're going to have 1/2 natural log of infinity plus 1, which I'm just going to call infinity, minus 1/2 the natural log of 1 plus 1, which is 2. And so we realize that this is an infinite number. And so therefore, because the improper integral diverged, therefore the series will diverge as well. And so the answer to this, after all of that work, is this diverges by the integral test. Okay, now we have the series, the summation from n equals 1 to infinity of 1 over n squared plus 1. And so we need to, first and foremost, prove that we can even use the integral test. So we're going to go through the same 3 conditions. Condition number 1, is it a positive function? Well, 1 over x squared plus 1. Once again, anything you square is going to be positive, plus 1 is still going to be positive. So this is always going to be greater than 0. So we can check that one. And then number 2, is it a continuous function? Well, this is similar to the last one, except it doesn't have an x on the top. So same reason, it's going to be continuous because there's no number that you could plug into the bottom that would cause you to be dividing by 0. So it is a continuous function. And then number 3, and a simple sentence can suffice on the AP exam whenever you have to prove that this is the method you use to prove divergence or convergence. Number 3, is it a decreasing function? Well, we could use the first derivative test here, or you could also draw the picture if you know what the function looks like, and that should be sufficient on the AP exam that you have proven that this is a decreasing function. If this is x equals 1, you can see that for all x's greater than or equal to 1, the function is decreasing. You could use the first derivative test as well, but that should be sufficient. So now we're going to come over here, and we are going to use the integral test to see what happens here. So we're going to integrate from 1 to infinity of 1 over x squared plus 1 dx. And so we recognize this to be the inverse tangent of x. That's our integral. And we're going to go from 1 to infinity, and I'm not going to use the limits. I'm going to be lazy. So not making a good example for you guys, but I'm not going to turn this into a limit problem. We're going to plug in infinity, so it's going to be inverse tangent of infinity minus the inverse tangent of 1. Well, if we remember what the inverse tangent graph looks like, it's going to have asymptotes here at pi over 2 and at negative pi over 2, and it's going to look something like that. So as x approaches infinity, this inverse tangent graph approaches pi over 2. So that's going to be pi over 2. And then the inverse tangent of 1, you have to think about what angle has a tangent of 1. So that's going to be sides of 1, 1, and root 2 because tangent is opposite over adjacent. So you're thinking about what angle would have an opposite side of 1 and adjacent side of 1. That's just 45 or pi over 4. So we essentially have 2 pi over 4 minus pi over 4, which is pi over 4. So, is pi over 4 a finite number? Yes, it is. So, that means that this series converges. Now, once again, let me repeat this. It does not mean that this series converges to the sum of pi over 4. We do not know what the sum of the series is. We just simply know that because the integral gave us a finite number, we can conclude that the series will converge to a finite number that we do not know. Okay, here's the last example for the integral test. And we see that we have the function, or excuse me, the series 1 over n, natural log of n. And I want you to notice that the term number starts at 2 to infinity as opposed to 1. And the reason for that is because we know that the natural log of 1 is 0, and then we'd be dividing by 0, which would not allow it to be a continuous function. So they started this one at 2 to infinity. So we're going to go through the same 3 conditions. Condition number 1, is it positive? Well, we can see that 1 over x natural log of x, the natural log function will never be negative, and, excuse me, for values bigger than 1, it will never be negative. For the values between 0 and 1, it is. But we are starting at 2, so we don't have to worry about that. And, of course, the x right here is going to make it greater than 0 all the time. So that is a condition that's met. Number 2, is it continuous? Well, we just said that the only value that x cannot equal here, x cannot equal 0, and x cannot equal 1, but the summation starts at n equals 2, so we're safe with that. And then number 3, we just have to prove that it is a decreasing function. And so we can see here that we can just use a little bit of logic. If you have 1 over x natural log of x, as x gets bigger, the denominator is going to be getting bigger, which means the overall number is going to be getting smaller. And so once again, that's just logic. If you have 1 over 10, well, the x would be 10, and so, but 1 over 10 is 0.1. If you have 1 over 100, well, the x just got bigger, but 1 over 100 is 0.01. The number is getting smaller. So we see here that this is a decreasing function. Not sure what the graph looks like, but we can use logic to see that it is a decreasing function. So now we're going to come over here and we are going to integrate this from 2 to infinity of 1 over x natural log of x. And we see that this is a u substitution problem. So we're going to let u equal natural log of x. So du is equal to 1 over x dx. And so x du equals dx. And so let me put a dx right there. So this is going to be the integral from 2 to infinity of 1 over x. And we called u our natural log of x. And dx is x du. And so here we see that the x's are going to cancel. And we're left with 1 over u, which I'm going to integrate to give me natural log of u. Now, u is natural log of x. So we actually have natural log of the natural log of x. And we're integrating this from 2 to infinity. So we're going to plug infinity in, and we have the natural log of, well, if you plug infinity here, the natural log of infinity is infinity. So then we have the natural log of infinity, which is infinity. All right, so minus, and you plug in 2, you get the natural log of 2, which is some number, and the natural log of that is just some number, we don't care, but it's just some finite number. Well, because this is infinity, that means that because the improper integral diverged, then that means that the series is going to diverge by the integral test. Now let me just put a plug in here that after you get practice, a lot of these are going to be mixed together. After we learn all 10 tests, they're going to be mixed together, and you're going to have to use some creativity to figure out which test you need to use on which series to figure out whether it converges or diverges. In some situations you can use multiple tests, and we're going to learn in the next couple weeks how to figure out which test is the best one to use. The last test that we're going to learn today in this video is called the P Series test. The P Series test. And this is probably one of the easiest, if not the easiest, tests to use to prove whether a series is convergent or divergent. And P Series test basically says that if you have some summation from n equals 1 to infinity of 1 over some variable, we'll just use n, to p, where p is a positive constant. P is a positive constant. Doesn't mean that that p must be an integer. It just must be a constant. It could be 2.3, it could be 4.5, but it is positive and it's a constant. And the P series basically says that if the exponent p is greater than 1, then the series is going to automatically converge. If the p is less than 1, it's going to automatically diverge. If p is equal to 1, that is going to automatically diverge. Now, when p is equal to 1, you have the series 1 over n, which is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, dot, dot, dot. That is a special version of the P series called the Harmonic P series, or the Harmonic series. And that is always going to diverge. So, just to have a little fun, let's use the integral test really quickly before we look at these two examples to prove that 1 over x diverges, but 1 over x squared converges. So on the left we have 1 over n, and if we, first of all, the integral test does indeed apply to this because, number one, it is decreasing, it looks like this. It is continuous for all x is greater than or equal to 1, and it is positive. So we're going to integrate real quick 1 over x dx, and we get natural log of x, and this is going to be from 1 to infinity. So we plug infinity in, we get natural log of infinity minus the natural log of 1. That's going to be infinity. That's going to be 0. We get infinity. That is an infinite number, so that means that because 1 over x diverged, the integral, then that means 1 over n is going to diverge because of the integral test. Now over here, we have 1 over n squared. Same three conditions apply because this one looks like this, and this one simply has even symmetry and looks like that. And so we are going to use the integral test again. So we're integrate from 1 to infinity of 1 over x squared dx. And so we're going to bring the x to the top. And we're going to add 1 to the power. And so we end up getting negative 1 over x. And we're integrating this from 1 to infinity. We are going to plug in infinity. So we get negative 1 over infinity minus negative 1 over 1. So negative 1 over infinity is simply 0 minus a minus 1, which is 1. Hey, that is a finite number. And so because the integral converged to a finite number, that means that the series will also converge. Alright, so now let's see how this P series works on two very quick and simple examples. Alright, in this first example on the left, we have 1 over n times n to the 1/2. So that's going to be 1 over n to the 3/2. And so 3/2 is greater than 1. And so this is going to converge by the P Series test. You're saying, is that it? Yeah, that's it. It's real easy. All right, this is one of the easiest ones that you will have to do. Here we're going to take the 5/2 in front of the summation, and so that way it won't get in our way. So we have 1 to infinity. And then we remember that anytime you have a radical, it's going to be the inside power divided by the outside power. So this is going to be n to the 5/4. And on the bottom, you have n squared. And so we also remember now that you're going to subtract the upper exponent minus the lower exponent whenever you are dividing. So over here we'll do 5/4 minus 2, which is 8/4. So we have upper exponent 5/4 minus 8/4, which is going to be negative 3/4. And because our exponent is negative, that means that it needs to be on the bottom. So this is going to be n to the 3/4. And 3/4 is less than 1. And the P Series test says if it is less than 1, it is going to diverge. All right, that's it, and we'll practice some more in class.